Okay, gang, welcome back. We're studying for exam 2. This is problem number 2. No, this is problem number 1, isn't it? This is problem number 1 on torsion. It's in chapter 5, okay? Level 5. Torsion. Now, I have picked a problem here. It's very similar to one you've seen. I've changed it a little bit. There's not a whole lot of these to pick from or to invent, and so I changed it up a little bit. We're going to work it again, okay? But I've asked you a whole bunch of different things. Number 1, find the reactions at the wall at A and B, okay? Find the reactions. Number 2, find the shear stress, right? Shear due to torsion in shafts A, B, and CD. A, B, C, D. Number 3, find the angle of twist of gear B. So a lot of equations at play here, right? We've got... Number 1, we've got gear ratios. Well, I'll put that with this. That's 2. That's terrible. Okay? That's just terrible. Let's do that again. Start over, Hanson. Gear ratios. And in this case, what's our gear ratio in this one, right? This one here is 4 times bigger than that one. That was 50. That one's 200. So we got a 4-to-1 gear ratio here. Okay, so how does that work? We got that. We got tau, shear stress, due to torsion, which is TC over J. Remember that guy. We got to figure J. Remember what J is? J is, for round shafts, pi on 2 r to the 4th. We got angle of twist, phi. And remember, what's the units for angle of twist? Bam! It's in radians, isn't it? Right? TL over JG. So the one torsion equation we pretty much don't have up here, we got everything else in the world, but the one thing we don't have up here is power transmission, okay? And I'll just quickly put that up there for you. Power transmission. P equals T times omega, or as my students call it, T booty. Okay, I don't know why they call that booty. I don't know. But this is just a fancy way. Usually, it's a fancy way to have to determine what is T, right? Because it's P divided by omega, and the T goes right there, right? So it's just a fancy way to make you do something else to come up with T, to put in that equation and solve that, right? The one tricky thing that you got to remember, it's not even tricky, but 1 HP, because America, equals 550 foot-pounds per second, right? That's the conversion for horsepowers, okay? So you need to remember that. So that's all the technology we'll use, except for this. We won't need that, but there it is. But that's really all the technology to solve a torsion problem on your exam. Let's put it to work and solve this rascal here, okay? Now, I think I want to start this problem off, just like all good problems, right? With a good old-fashioned free body diagram. And I'm going to draw a free body of this shaft, and then I'm going to draw one of that shaft, okay? So, big gear first. Okay, big gear first. Yes, I didn't put teeth on my gear, so just get over it, okay? Really. I mean, serious. Okay, let's see here. Here we go. Here's little shaft. All right, what do we got? Let's get a red pen again for our stuff. Okay. Now, what we got here is, number 1, I've got this. 500 Newton meters. And if I'm looking at it this way, that's rotating me. Well, that's counterclockwise, right? So what that's going to do, number 1, for the wall, is wanting to go the opposite direction. I'm going to call that RD, the reaction at D, the reaction moment at D. Now, as this thing wants to rotate this way, this other gear over here says, I don't want you to rotate. I'm going to resist and push on you back the opposite direction. So right here, there's like this pushing force. It's a tangential force that's trying to spin that gear back the opposite direction, isn't it? And that comes from the teeth over here. Gear push on teeth, teeth push on gear, right? Now over here on this gear, I've got exactly the opposite of that guy, okay? Pushing on that gear, trying to rotate it that way, which means that over here at the wall, I've got RA trying to, it has to oppose that, right? This is trying to rotate that shaft. Again, if I look at it, counterclockwise, so this has to rotate clockwise to prevent that. So I got those things going on, okay? Now, that should allow me to write some of the moments for these two guys here, okay? So number one, we'll try this guy here. If you add up all the moments on this thing, it should equal 0 because it's not spinning, because it's wall. It can't rotate, right? So what do you have trying to do me here, to spin me? Okay, so I've got RD, which goes, okay, RD, that's positive, and then minus 500. Now that's in Newton meters, okay? So be careful this next bit. I've got F, but F is not a moment. I've got to multiply it by distance. Well, the distance is here, right? Force times distance. And that distance is 25, isn't it? Okay? So that's going to be plus 0.25. No. 0.025 F, isn't it? Right? Because it's a radius. This has a diameter of 50. The radius is 25, right? Because we just want from here over. Well, there you go. Okay? Now, well, let's just leave that alone. Let's come over here, do the exact same thing for over here. What do we got over here? Well, I got this guy going clockwise, so minus RA, and then plus F times how far away? Well, the diameter is 200, so the radius would be 100, so that would be 0.1. And why did I change it to meters? Because that guy right there was in meters, right? So now my units are all the same. So RA, well, let's just do F, shall we? F equals, calculator. So F equals, it's move the RA to the other side, and then there's a 1 in front of the RA, right? Divide 1 by 0.1, it goes in there 10 times, doesn't it? 10 RAs, okay? Let's go over here now and substitute F in for over there. So we get RD is equal to 500 minus 0.025, right? I just moved this stuff to the other side, times F, which is 10 RA. Okay. And so, well, we can do this, can't we? This is going to be RD is equal to 500 minus 10 times that is just 0.25 RA. So there is a relationship between RA and RD. That doesn't help at all. Okay, well, shoot. Maybe this will help, okay? Let's look at this guy right here, the gear ratios, okay? Now we have to make this statement true. We got two gears. We got gear C, we got gear B, okay? Gear C, gear B, B, C, okay? Now we know these are the gear ratio is 4:1. Let's just say this. If this guy here rotated one time around, what would this do? Well, it takes 4 of those. This go around one time. So that goes around one time. That only goes a fourth. So to make this statement true, right, the rotation of gear C equals the rotation of gear B. How do I make that statement true? And you make that statement true, here it goes. The big number in your gear ratio, 4, okay, goes on the big gear. So put a, guess what, 4 right there. Now, does that make sense to you? It might not make sense, right? If this makes one rotation, then how much does B make? If this is 1, then what is B? divide 1 by a 4, it's a fourth, isn't it? So I can just do a quick little substitution in there and kind of sanity check my relationship there. So this relationship here is what I need to do next to kind of come up with a second equation for this here, okay? Now, one thing I need to know here is I need to know G, okay? And I'm going to give you G. G, the shear modulus of rigidity, is, for this material, 200 gigapascals. I really don't have to give it to you, but I need it for, well, I'll need it for in a minute here, okay? Okay, so now here's our phi relationships, okay? So phi, what is phi? What is phi? Oh, it's TL over JG, isn't it? So what I'm going to have is this. I'm going to have TL over JG for this shaft is equal to, or for this gear rather, TL over JG for this one up here. But what do we know? That B is 4 times. So this guy down here, it's 4. Let's say this will make this one B. This is gear B over here. Okay? There's a 4 there. There's a 1 over here, right? Okay? This is gear C. All right, next. Okay? Let's just go for this guy right here. What is the torque that gear C is going to see? Okay? Now what we can do, remember, cut it in half. So let's cut the beam in half and let's cover it up. Now how much torque is in that shaft right there? It's RD, isn't it? Okay? So RD times, got to make our units work out here, gang, times L, which is 2.25 meters. Let's put everything in millimeters, okay? 2,250 millimeters divided by J. Ooh, we got 2 J's here, don't we? Okay, this first J, this guy right here is, because J is pi over 2, r to the 4th, is pi over 2 times 15 to the 4th. That's millimeters to the 4th, okay? Got it? Okay, now let's go to this guy over here. We got our 4 there, don't forget about that guy. Times T, what's the torque in this shaft? Again, cover it up. What do you got? It's RA. I know, right? RA times L of this guy, which is 1,200 millimeters. Okay? TL over J. Oh no, what's J? Same thing. Pi over 2 times, that one's 40. So the radius is 20 to the 4th. Millimeters to the 4th. Okay? That's going to give us a relationship between RA and RD, isn't it? Let's see what that gives me here. On 2250. Oh, man. Divided by 15 to the 4th power equals times 2 equals divided by 3.14159 equals, okay, equals 0.028294236. I'm going to put them all in there, okay? Now let me do that side over there. 4 times 1,200 equals divided by 20 to the 4th power equals times 2 equals divided by 3.14159 equals 0.019. Okay, I'm going to take that and divide it over here. Okay, I'm going to take that number and divide it into that number. Okay, so 0.028294236 236 divided by, answer is 1.48. So that whole thing boils down to 1.48 RD equals RA. Okay? So I'm going to plug that business in for RA over there. So what are we going to get? We get RD is equal to 500 minus 0.25 times 1.48 RD. Okay, so 1.48 times 0.25 equals 0.37. Now let's move that to the other side. Whoop. So I got 0.37, and then I move it over here. There's a 1 in front of him, right? So that becomes 1.37 RD equals 500. RD equals 500 divided by answer equals 1350. No. 500 divided by 1.37 equals, how about 364.96? Okay. Now, how can I get RA? Well, I can plug that number into there and solve for RA, or, I mean, RA should just be that number times 1.48, right? Times 1.48. You should get the exact same thing either way you go. 540.14. So let's go 540.1. And that is, what is that unit? That is newtons, right? Newton meters. Duh. Okay, boom. Okay, I think there's a reaction at A and D. That is the answer to part A. What's the answer to part B? What's the shear stress in A, B, and CD? Well, here's our equation right here. Let's make us a little bit of room here. Let's do it right up here. Okay. We got let's do AB. The shear stress is TC. Now what's the torque in that section there? The torque in that section is RA. So 540.1 Newton meters. Now I don't want that meter in there. Let's get rid of that guy. There are 1,000 millimeters in a meter. And then we've got C. What is C? The distance from the neutral axis to the outside of the part, which is a radius, which is 20 millimeters. Okay. Divided by, this is tau AB, divided by, well, J. Okay, so that's just pi on 2 times 20 to the 4th millimeters to the 4th, right? And look, millimeters to the 4th, there's 2 of them. Cancel out with 2 of those. The meters cancel out. It's going to leave me with newtons over millimeters squared, so my answer is going to be in what, y'all? Megapascals. That's right. Okay? So, 540.1 times 1,000 equals times 20 equals times 2 equals divided by 3.14159 equals divided by 20 to the 4th equals 42.98. Let's just call it 43, right? So tau AB equals 43 megapascals. Groovy. Okay? What about the next one? All right, I'm going to erase your equations of the day over here so we can finish our problem. Oh, now we not know what we're doing. Okay, so tau BC equals, same equations, okay, but now we have what? RD, the torque has changed. So that's going to be 364.96 times 1,000 times C, which is 15, divided by pi over 2, 15 to the 4th. So tau BC is equal to, here we go, 364.96 times 1,000 times 15 equals times 2 equals divided by 3.14159 equals divided by 15 to the 4th equals 68.84. Now, sanity check, you might ask yourself, how come the stress is so much higher in this one than that one? Do you know the answer? I think I do. And it's because this is a much smaller cross section, right? So it's going to be subjected to a higher shear. That one's got a lot more material to carry the load. That one's going to be worse, isn't it? Okay. All right. And now what do we got left? What do we have left? Oh, find the last one. Find the angle of gear B. Okay. So phi for gear B is going to equal, well, it's however much this shaft right here is going to rotate is how much B is going to rotate. So I just need to do phi for this section of shaft right there. And remember, it's TL over JG. So T, the torque in this shaft, is RA, which is 540.1. Okay? And again, that's Newton meters. So I'm going to multiply that again by 1,000 mm's per meter. And then L is in what? 1.2 meters. I'm going to call it 1,200 millimeters. Okay? Divided by, because this, what's the unit for phi? Radians. So all of my units, every single unit in here needs to cancel out, right? Okay, over J, which is pi over 2 times 20 to the 4th millimeters to the 4th. That's a lot of millimeters. And then G, right? What is G? Gigapascals. Let's see. I don't want it in that. I want it in megapascals because megas, right? 200,000 is newtons over millimeters squared. There's my newton. There's all the millimeters. Everything cancels out. No units left. That's radians. So last answer of the day. Remember, this is in radians, not in degrees. 540. Woo, clear. 540.1 times 1,000 times 1,200. Well, not 12,000, equals, and then times 2, and then divided by what? Pi, 3.14159 equals, divided by 20 to the 4th, 20 to the 4th, and then divided by 200,000. 1, 2, 3. 0.01289. 0.0129 radians. And there you go. Monster problem, y'all. Monster problem. Good problem, though, because it has all of the sections that we need to test you over torsion in one problem. Man, that could show up on the exam, couldn't it? Okay? All right, I hope this helps. I hope you make 100 on your test. Stay tuned for the next sample problem for the test, okay? Let's go.